This is Paul Humke, and this is the first video that's got a little multivariable calculus content to it. I thought I'd talk a little bit about what we're going to do in the entire course. And multivariable calculus extends the same ideas that you dealt with in regular calculus. There are basically two of them, derivative and integral. For the derivative in one variable calculus, geometrically, it tells you something about finding tangent lines to curves or graphs of functions. It tells you about the concavity of the function and so on. These are what the derivatives will tell you. The rate of change is, in general, what the derivative is interpreted as. And the integral is used to give you geometric information of a different sort. It gives you the area under the curve, or it gives you the arc length of the curve and these sorts of things. Now in higher dimensions, we're going to do the same thing in various contexts. One of them is we will look at real valued functions. So these are functions that begin, say, in maybe R2 and map into the reals. Real valued is the fact that the range is contained in the reals. So that's what real valued functions will be. And we'll do some of the same things for graphs of real valued functions. We'll graph these things and we'll look at their tangent surfaces. Now the graph of such an object will be a two-dimensional object, and the graph lies in 3 dimensions because you have two domain variables, x1 and x2. That's what this means here. This 2 exponent means you've got 2 domain variables, and you've got one range variable. If there's several of them, you use y1 and y2, but if there's only one, then you use y. Inherent in here is some equation, y equals f of x1 and x2, and you know that for each ordered pair x1 and x2 there's only one y. That's what it means to be a function, passes the vertical line test. So the graph for these is some kind of surface. And we will look at tangents to this surface. Now a tangent is not necessarily a line. Lines can be tangent to the surface, but the tangent surface itself at a given point is a plane. So we'll be looking at tangent surfaces to real valued functions whose domain are two-dimensional vectors. But we will also be looking at more general tangent surfaces for real valued functions, where the function will map 3 dimensions into the reals. Such a function might be temperature. Temperature function takes 3-dimensional coordinates and gives you a temperature at each of those points. And we'll look at tangent surfaces to those. Now, a tangent surface for such a function is a tangent to the graph, but the graph lies in 4 dimensions. 3 dimensions, x1, x2, and x3 from the domain, and 1 dimension from the range. So the tangent surface will be difficult to graph. The graph itself will be difficult to graph because it's in 4 dimensions. Actually, we can graph it, but understanding what that graph means visually is very difficult. We're 3-dimensional folks. So even though we can make some sort of device to allow us to see this 4th dimension, it doesn't easily provide us information like the 3-dimensional case does. But we can still find tangent surfaces. We'll use a derivative and we'll do that. So real valued functions are important for us. We'll be interested in surface area of these things and doing various operations with regard to the surfaces. We'll also look at vector valued functions. So we'll begin with a function f, say maps the real line into the plane. Now we'll have one domain variable, and we'll have two range variables. So these are vector valued functions. Sometimes these are called parametric functions, and x is the parameter. And here we won't be looking at the graph so much, but we'll be looking at the range. So in such a picture, the function f will take the real number line and move it in some way into the plane. So maybe it bends it around in such a position. So now we'll be looking at the trajectory or the range of this function, and we'll be interested again in tangents and so on. We'll be able to measure the curvature here, and these are some of the things that we'll be doing with vector valued functions or parametric functions of one or several variables. In general, these are the things that we will begin doing, and there will be more later on. But I'd like to begin with a little of the language that we'll use. And our language is the language of linear algebra. We will describe things in terms of the language of linear algebra and use vector notation that you developed in linear algebra. And some of that linear algebra you developed in your Calc 1 class. But the two things I'd like to talk about first of all, and we'll talk about this in class on Friday, are the dot product of two vectors and the cross product. Of two vectors. So in general, if I'm in a multivariable calculus class the first day, what I will do is I will say, well, I will give you two vectors, say vector u and vector v, and let's suppose that both of these vectors are vectors from a plane, and I'll ask, what is the dot product of these vectors? What is the dot product? So what is the dot product of these two vectors? I know. Snow, what are you doing here? Well, you told me to come. Well, yes, I did, yes. And where is Ohm? I told him, and he didn't show up. Okay. But in this case, that dot product, how do you do it? What is it? Well, you do this. You take u1 v1 and add it to u2 v2. So what are these u1 and u2? What are the v1 and v2? What are they? Okay. U equals u1 u2, and v equals v1 v2. Yes, you got it. Don't write that line, that's not a vector. I know, it was a mistake, Snow. So I see, so this is how it goes. You just multiply the firsts together and the seconds together and add them up. Yep, that's it. That's all there is to it. Well, not exactly. That's not all that there is to it. There's a little bit more to it. This is an operational definition of dot product, but there's also a different way, a geometric definition. Do you remember that? No. Well, works like this. The dot product, u dot v, is the length of u. I can compute that. I know how to compute that. That is good. Times the length of v times the cosine of the angle between them. And this is actually why it's important. Because of that cosine term right there. The cosine term allows you to find the angle between two vectors. Because you can compute the dot product easily like this, up above. You can compute the lengths, and the only variable is theta, the angle between them. So you can compute that. Yeah, I did that. That's good. I forgot. Well, it happens, yeah. Okay, so this is the dot product between vectors, and we'll use it quite a bit. In particular, two vectors are perpendicular when and only when their dot product is 0, and neither of them is 0. And the dot product works easily in any dimensions. So if you take any r, say 32 space, the dot product works the same. U dot v is u1 v1 plus u2 v2 plus dot 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 plus u32 v32 amen. And the same geometric holds that u dot v is the length of u, length of v, cosine of the angle between them. So knowing that allows you to find the angle between any two vectors in any particular space. And that's one of the ways we'll use it. We'll use it a lot that way. And we'll use it also because of this perpendicular property that u is perpendicular to v if and only if their dot product is 0. Cross product is a little different. If you take two vectors, say we're in R3, this is where cross product actually begins. Dot product begins in any space, even R1, it just means the product. But cross product begins in R3 and then extends in other ones. But if you take u and v in R3, then the cross product between them is defined as the determinant, and I'll write determinant with vertical lines. I, j, k are the coordinate. These are the coordinate unit vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is the determinant of a unusual matrix. It's a 3 by 3 matrix, but these are vectors. And so what this means in particular is in the ith coordinate, or the first coordinate, you put u2v3, this times this, minus this times this, minus v2u3. And similarly for the j and the k coordinates. Now, this vector that you get, this doesn't give you a number, this gives you a vector because of these I, j, k. So this is a vector. And this vector is mutually perpendicular to both u and v, and that's how it's used. And the reason is this. For example, if we take u, and we take the dot product with u cross v, because of the way determinant works, this will be equal to this determinant, u1, u2, u3, u1, u2, u3, v1, v2, v3. It's easy to check that this dot product is this. It just replaces the I here with the I coordinate of u, u1, the j with the j coordinate of u, and so on. And now this determinant is clearly 0 because these two rows are the same. Oh, yeah, these two rows are the same. So any matrix that has two rows that are linearly dependent has determinant 0, and so this determinant has two rows identical, and so you get identically 0. And then this tells you that U is perpendicular to U cross V. So this is a way of finding a vector that is perpendicular to two given vectors. And this is very helpful when looking for specific bases in 3 dimensions. The easiest bases to work with are really bases that are where the vectors are mutually perpendicular, and the Gram-Schmidt process does this for you in linear algebra, and we use it here. A little later in the course we will use it, and it'll be of invaluable use to us. So have a look at the cross product, recall some of these things, and on Friday we'll work a few problems on a worksheet on cross product and dot product. I'll ask you to see if you can find what the cross product is in 4 dimensions and higher, how that can work, and we'll go from there. So have a look at this video before class on Friday. On Friday we'll have a worksheet and I'll assign some homework problems. Hope you had a good introduction to Olaf, and see you soon.